So we got the asymptotic formula for saddle point approximation. Here it is for Laplace type integrals. It looks very familiar to the previous expression for Laplace type integrals. You recognize the square root type thing. Well, the only difference from real valued case is that instead of f prime prime, now we have the modulus of f prime prime. Well, what next? Well, the principal exponential look the same. And here you have additional IB factor, where B is the angle of the steepest descent path. So what could be the simplest possible application? Well, let's discuss the most interesting thing, the physics application. So what we are going to consider is a particle inner linear potential. So here is our potential profile. So what it is? So the linear line basically means that our potential energy, U of x, is equal to alpha x, where alpha is a slope. So physically, it's the basic gravitational potential. And here we have an impenetrable wall. Well, actually, it's in our case, we may interpret it as an impenetrable floor. So it's kind of a ball which bounces from the surface of the ground, I would say, right? So the energy levels of such a system, so the potential is finite, and the energy levels are quantized. And our goal is to find the energy levels of such a system. And in addition, we will consider quite unusual particle, the particle with a linear spectrum. Epsilon is equal to Cp, so it's kind of relativistic particle. And C, well, it's sort of a light speed, for example. All right. It happened that we can't find the spectrum exactly. So we have to use some kind of approximation. And what we will effectively use is so-called semi-classical approximation, meaning that we will be able to find the formula, analytical formula for energy levels for large values of n, where n numerates the corresponding number of the energy level. All right. So let us introduce the main large parameter of our system. So it's epsilon squared, where epsilon is the energy of the corresponding energy level, over C alpha. And this is going to be the large parameter in our problem. All right. So how do we start this problem? Well, first of all, we write down the Hamiltonian. Hamiltonian is an operator, and you see, due to the fact that we have this unusual kind of spectrum, so it's not your typical p squared over 2m. It's linear. So we'd better work actually in momentum representation. So here we go. So C modulus p. Well, right now, probably it's better to write down it's in operator form. Plus, so it's a kinetic part and potential part. And since we want to use the momentum representation for our Hamiltonian and our wave function, so our momentum operator becomes just a C number. And our coordinate operator, well, probably you remember, is I h bar, where h bar is Planck's constant, d over dp. Well, we'll work in so-called God-given units. So we'll put h bar is equal to 1. OK, so let's start. Probably you know, well, I hope you know, that the wave function in coordinate representation and in momentum representations are related by their Fourier transform. So our goal would be to find this Fourier component of our wave function, or the wave function in momentum representation. So let's write down the final Schrodinger equation for our problem. Here it is. So it's C modulus p AP plus alpha I, potential term, alpha I d over dp, so dAp over dp, and it's equal to the energy times AP. Here we go. And now you clearly see that it's a simple first-order differential equation, which is quite easily solved. So the only subtlety here is that we have, instead of just momentum, we have the modulus of the momentum, right? So we have to consider two cases, positive and negative momentum. Here they are. So modulus of P is obviously is equal to P if P is positive, and minus P if P is negative. All right, so you may write down the solution of this equation by yourself just in a minute. So right, here is our equations for positive and negative momentum. Here is our, again, connection between the coordinate function, the wave function in coordinate representation and in momentum representation. So here we go. So, well, the solution of the first differential equation, well, it's easy. You can easily integrate it. And here it is. So for it's c, some integration constant, times exponential function. And the exponential function is like that, minus I over alpha, epsilon p minus cp squared over 2. And for negative momentum, the only difference between these two equations, as you see, it basically c is changed to minus c. Well, okay, pay attention. It's a capital C, and this one is a small c, the speed of light. Okay, so don't get confused. Right, so technically we have to write this c1, and here c2, another integration constant. So plus cp squared over 2, as it should. Okay, but our wave function, even in momentum representation, should be a continuous function of p variable. Why? Because, well, we have this differentiation sign in our Schrodinger equation, and you can easily convince yourself that AP should be a continuous function. And that means that it can't have these drops of values. So C1, so AP at P tending to plus 0 is equal to AP at P tending to minus 0. Right, and that means that C1 is equal to C2. Okay, now we have this relation between the wave function in coordinate and momentum representation. We have an impenetrable wall here, and that means that the wave function, so the particle can't penetrate here in this region. And that entails that psi of x at x is equal to 0, so at this ground level, should vanish. And this is basically our boundary condition, which will give us the quantization rule for energy levels. All right, so psi of x, psi of 0, as we see here, is simply the integral of our wave function in momentum representation over the whole values of momentum. Right, so this is our quantization condition. Now we are ready to compute actually our wave function. Okay, so here is the expression, and we basically plug in these two expressions into our quantization condition and get the energy levels.